All right, hey everyone. Welcome to the second to final lecture in algorithmic game theory. Hope everyone's doing all right. I'm gonna briefly unmute you all so we can all say hi. Hey everybody.
Hello.
Hi.
All right. So in the last couple of lectures, I want to talk about two interesting research topics that are not primarily focused on algorithmic game theory, but which both have some connections: differential privacy and algorithmic fairness. These are usually topics that people study with sort of non-game theoretic motivations. Differential privacy is a privacy-preserving technology. Typically, you'd want to solve some data analysis or machine learning problem with some kind of rigorous privacy guarantee that would promise, for example, that although we could learn something useful about the data set at large, nobody would learn anything specific to any particular individual. Similarly, in algorithmic fairness, we're concerned about designing automated systems which are going to make important decisions about people, things like lending and criminal justice, for example, and we want to make sure that they don't treat people unfairly. And those are both huge topics, and you could teach a whole course on each of them, but both of them have some connection to algorithmic game theory. And in the last two lectures, I'm going to touch on just a little bit of that connection. Okay, and these connections will go sort of in opposite directions. So today I'm going to talk about how you can use differential privacy as a tool to solve game theoretic problems. And next class, I'll think about how you can use game theoretic analyses to reason about algorithmic fairness. Okay, so just as we have done for the last 5 or 6 lectures, in this lecture, and this is the last such lecture, I promise, we will again use digital goods auctions as our test bed to try out new techniques in mechanism design. It's been a fruitful test bed, and we're going to keep trying to exploit it. So let's just remember some stuff we know about digital goods auctions. In particular, if you remember back 2 lectures ago when we used the polynomial weights algorithm to derive an online auction for digital goods, we were able to obtain a dominant strategy truthful mechanism that had the revenue guarantee that it could, up to some additive error, approximate the revenue of the best fixed price in hindsight. And that additive error scaled with square root of n, square root of the number of bidders. And that was actually sort of the best we have done so far in this setting, right? So last class we studied a harder problem, one in which we actually need to give a dynamic pricing instead of just an auction. So there was more limited feedback, but we got a worse bound. We got a bound that was more like n to the 2/3 here instead of root n. And in our first lecture on digital goods auctions, when we derived the random sampling auction, that was actually, at least for large n, like a substantially worse bound. That was a multiplicative approximation of 4 instead of an additive approximation that hopefully becomes negligible as opt gets sufficiently large. And so in this class, what we're going to try to do is we're going to try to do better, but we're going to try to do better by giving something up. So what we'd like to do is we'd like to obtain a bound that is of the same form as this one. We'd like to approximate the revenue of the best fixed price in hindsight using an auction, but we would like the additive error to be like better, hopefully a lot better than square root of n. But we might have to give something up if we're going to ask for a substantially better additive error. And what we're going to give up is exact dominant strategy truthfulness. Instead, we'll try to get approximate dominant strategy truthfulness. And since we're talking about asymptotics in the error, we can also talk about asymptotics in the approximation to dominant strategy truthfulness. We can ask for something that I'll call asymptotic dominant strategy truthfulness, where maybe we will say that it is an epsilon approximate dominant strategy for bidders to bid truthfully, where epsilon is also a parameter that goes to 0 as the number of bidders n grows large. So in the limit, as n grows large, we're going to get some, hopefully a very good revenue guarantee, and it will also be in the limit at a rate that we can control a asymptotically dominant strategy to tell the truth. Okay, so that's sort of the goal for this class. And the tool that we're going to use is differential privacy. So differential privacy is a tool that's been developed primarily in the data privacy literature. That's why it's called differential privacy. It's actually pretty cool. We'll touch on it only briefly in this lecture, but if you're interested in these kinds of things, there's a lot you can read up on it. It's sort of a rigorous mathematical guarantee that you can, it's a property you can prove about an algorithm, and it offers some kind of formal promise that nothing can be learned about an individual from the output of a data analysis that couldn't have been learned without his participation. And you can do all sorts of useful and interesting things subject to this guarantee. And it's become a sort of real technology as well, not just an academic curiosity. It's sort of deployed widely at Google, on the Chrome browser, on iPhones, and it's being used to protect all of the statistical products released as part of the 2020 census. Yeah, anyways, differential privacy is a whole field you could read up on if you're interested in those kinds of things. But here we're going to use it as a tool to solve this digital goods auction and try to get a better revenue guarantee. And we'll see what it is in a couple of slides, but informally, the reason there's a connection between mechanism design and differential privacy is that the privacy guarantee that differential privacy promises is that there should be essentially no observable differences in, when I compare the real world in which your data is used as part of some data analysis, and in sort of an idealized world in which everything is the same as in the real world, except that your data was removed and was not used as part of the analysis. And the difference between sort of the real world and the idealized world corresponds exactly to the difference that you can sort of affect as a single bidder in an auction, basically a unilateral deviation. And that's going to be the root of the connection between differential privacy and game theory. Okay, so at a high level, what's our approach going to be? So remember, we're trying to compete with the best fixed price in hindsight. The best fixed price in hindsight, given a collection of bids, is just the price P that maximizes the price times the number of people who are willing to pay the price, the number of people whose valuations are greater than the price. And so you could, ask yourself, and we did ask ourselves, at the beginning of this segment of the course, why don't we just look at all of the bids and compute the price that maximizes revenue and charge that? And the reason is that this is a mechanism that is not dominant strategy truthful, and in fact, it's not even a little bit dominant strategy truthful. This is a mechanism that will be highly manipulable by at least one of the bidders. And that's because for any particular collection of bids, we argued early on that the price that will maximize revenue is actually equal to one of the bids. That is, if I just look at the bids that I've received and say, okay, like suppose people are bound to honor the bids they've placed, and I just say, okay, well, which price would maximize my revenue amongst these placed bids? we argued that the price will always be equal to one of the bids of one of the bidders. There will be some bidder I star who will be chagrined to learn that the auction has chosen his bid as the price, and it's gonna say, lucky thing, you bid $100.23. That turns out to be exactly what the price is. And in particular, that bidder will have a strong incentive to change his bid because it will change the amount of money that he has to pay. And it was this observation that sort of caused us to have to go through all of the contortions that we did designing all of these different kinds of mechanisms, either the random sampling auction or these auctions that handle bidders one at a time. In all of these cases, the way that we were able to get dominant strategy truthfulness was by going through contortions to somehow compute prices to charge bidders that were independent of the bids they reported, right? Like this was the whole premise of the random sampling auction, that we would split people into two groups. We would compute prices on the first group and charge them to the second group and vice versa. Similarly, in online auctions, we computed prices as a function only of the people who'd come before, right? Like all of the hard work we had to do was to try to figure out what good prices would be to charge without actually having those prices be a function in any way at all of the people, of the people's bids who we were trying to charge the prices to. And so the question we're going to ask in this lecture is, well, okay, I can't just go and compute a price that optimizes profit on the bids and charge that, because that'll be an extremely sensitive price of an extremely sensitive function of the bids. There will be like one bidder who can unilaterally just change the price by changing his bid. But what if we squint a little bit? What if we could somehow compute a price that wasn't independent of the bidder valuations, but was somehow almost independent of the bidder valuations, whatever that means? Right? Like if I could compute a price that was almost independent of everyone's bid, would that somehow make the auction almost truthful? Right? Like this is sort of a ill-defined question at the moment, but right, the starting observation is we get a truthful auction if the price we charge to each bidder is independent of their bid. Can I get an almost truthful auction by computing a price that is almost independent of bidders' bids? Okay, and so that's sort of the question that's going to motivate what we do in this lecture. Okay, and our tool is going to be differential privacy, and so let me now define for you what that means in this context. So first of all, borrowing some terminology from the privacy literature, let's call two vectors of bids. Okay, a vector of bids is just a bid, one for each of the n bidders. Each bid is just some number between 0 and 1. Let's call two such vectors of bids neighbors if they differ in the bid of just a single agent. Meaning, there's some bidder I such that maybe maybe bidder I's bid is different between V and V prime, but everyone else's bid is the same. Okay, let's call these neighboring bid vectors, and neighboring bid vectors are sort of a natural thing to consider because they result from a single player making a unilateral deviation. Okay, so if I've got n bidders and there's some bidder 5 who's considering whether he should truthfully report his value or whether he should misreport, then in world A, if he truthfully reports his value, and in world B, if he misreports, but everyone else stays the same, everyone else does the same thing in worlds A and B, then we'll call the two bid vectors that result in these two worlds neighboring. And now in this context, here's what differential privacy is. Okay, so suppose we've got some mechanism a mechanism here is just going to be an arbitrary mapping from bid vectors to outcomes, and we're going to allow it to be a randomized mapping. Okay, so in sort of a pretty abstract space, a mechanism is just some randomized algorithm. It takes as input bids of all of the bidders, and it chooses some outcome. Okay, and we will say that it is epsilon differentially private. Differential privacy is going to come with this parameter epsilon if for every pair of neighboring bid vectors, v and v prime, okay, and for every outcome O that the mechanism might choose, if we look at the probability that the mechanism actually chooses some outcome X when we run it on bid vector V, this should be similar to the probability that the mechanism chooses the same outcome X when we instead run it on this bid vector V prime, where similar means within a multiplicative factor of e to the epsilon, where epsilon's our privacy parameter. And why e to the epsilon? That's kind of a weird term. Well, think of epsilon as being some small number, right? Definitely less than 1. So think about it as being, 0.01 or something. And in that case, e to the epsilon is kind of just 1 plus epsilon. It's roughly 1 plus epsilon. In particular, if epsilon is less than 1, then e to the epsilon is sandwiched between 1 plus epsilon and 1 plus 2 epsilon. So, think of the definition really as saying, if you unilaterally change your bid, then you are not going to change the probability of any outcome by more than a 1 plus epsilon multiplicative factor. And, why do we use e to the epsilon instead of 1 plus epsilon? It turns out that when you reason about complicated differentially private algorithms, there are good reasons why mathematically it's more convenient to keep track of this parameter, e to the epsilon, than 1 plus epsilon, essentially because when I multiply exponentials, the parameters add up. But that won't be relevant in this lecture. Okay, so the definition is actually pretty simple. It just says, okay, a mechanism is differentially private if for every bidder and for every vector of bids that they might make, if you unilaterally change your bid, then it doesn't actually change the probability of any outcome by much, okay, where by much is parameterized by this number epsilon. Okay, so there's some notation on the slide, but the idea is basically pretty simple. It's that a differentially private mechanism cannot be a sensitive function of any single bidder's bid. Are there any questions about the definition before we go on? Because we're gonna, throughout the rest of the lecture, think about first the consequences of what happens if we derive a differentially private mechanism for some auction problem, and then think about how to actually do it. Okay. So, so far we've defined a privacy definition, but remember, we're just trying to solve some auction problem. There's plenty of interesting problems out there where your goal is explicitly to promise some kind of privacy. And maybe let me just add here, why is this thing called differential privacy? Well, if the probability of any outcome doesn't change by very much, if a single user changes their data, then that means that I can't make any inferences that are specific to the data of a single individual, because there's essentially no statistical test that can differentiate between the world in which the thing that I observed, the outcome of the mechanism, was a function of a particular individual's data, which in principle would allow me to make inferences about them, and the world in which the thing that I observed wasn't a function of their data, in which case I couldn't make inferences about them. And so essentially, a condition like this is what you need in order to promise that outside observers can't learn anything specific about a particular individual because of their participation in a computation. So that's why this this mathematical constraint here deserves the name privacy. But okay, there's plenty of situations in which you might care about privacy, but we're not in one of them. Our goal here is purely to design an approximate dominant strategy truthful mechanism that has good revenue properties. So let's go back to mechanism design and just remind ourselves what we mean by approximate dominant strategy truthfulness. And it's pretty simple. So again, a mechanism, some arbitrary randomized mapping between bids, you can place your bids, the mechanism will choose some outcome, and you as the bidder will have some utility function. It's parameterized by your value for the good, say. It's parameterized by your value for the good V, and of course the outcome that the mechanism chooses, like do you get the item or not. And again, you might decide to tell the truth. Okay, we'd like you to tell the truth. That's the thing we're trying to incentivize. Or you could, if you wanted to, misreport your evaluation to the mechanism. You could misreport your evaluation as VI prime instead of VI. And since it's a randomized mechanism, when we ask, what is your utility for reporting your true valuation VI or for misreporting your valuation VI prime, we now have to talk about your expected utility over the randomness of the mechanism. And what approximate dominant strategy truthfulness means is that no matter what everyone else reports, it should be, over the randomness of the mechanism, an approximate dominant strategy for you to report truthfully. Meaning, if you report truthfully and I consider your expected utility over the randomness of the mechanism, this should be at most epsilon worse than your expected utility over the randomness of the mechanism if you misreport. Okay, so maybe there are situations in which by reporting VI prime instead of VI, you can gain a little bit in expected utility, but not much. You can gain at most epsilon. Okay, and so maybe this is close to maybe this is almost as good as dominant strategy truthfulness, at least if we can make epsilon very small, and at least if we can imagine there's some small disincentive for misreporting. Maybe you have to spend a little bit of effort to figure out what would be the best misreport, or maybe you risk some reputational damage by misreporting. And if the benefit of misreporting is sufficiently small, then maybe it's not worth it. That's sort of the premise for approximate dominant strategy truthfulness. And we're really only going to be interested in it when epsilon is very, very small. So we're going to, in the end, ask for mechanisms that are what I will call asymptotically dominant strategy truthful, where we can actually take epsilon to be some function of the number of bidders that goes to 0 as the number of bidders grows large. Okay. So the heart of the connection here, the reason why differential privacy is going to be useful for us, is because of a pretty simple observation that differential privacy is going to automatically guarantee approximate dominant strategy truthfulness. That is, if I design an auction mechanism that is epsilon differentially private, then it is also going to be epsilon approximately dominant strategy truthful. Which means that we can, again, this is sort of a running theme in this class. We did it also, in a couple of other settings, in particular when we were talking about single parameter mechanism design. We can, again, reduce a mechanism design problem to a purely algorithm design problem, right? Like once we establish this connection that differential privacy implies approximate truthfulness, thinking about how to maximize revenue subject to the constraint of approximate truthfulness will turn into the purely algorithmic problem of thinking of how to design differentially private algorithms that are good at maximizing revenue. And so this is the theorem. No matter what the mechanism is, if it's epsilon differentially private, then it's also epsilon approximately dominant strategy truthful. Okay. And so let's prove it. It's actually almost immediate. So it's gonna follow basically by writing down the definitions, right? So what do we need to prove? Well, we need to prove that no matter what buyer we're interested in, no matter how people bid, no matter what the buyer that we're interested in values the item at, the gain that he can get by misreporting can only be very small, can only be epsilon. And so let's fix all of those things. We'll fix a buyer, we'll fix a valuation vector, a set of bids for everyone else, and we'll fix a utility function for that buyer. And we're interested in, okay, well, what's the relationship between his expected utility if he tells the truth and his expected utility if he lies? So first, let's just write down what is his expected utility if he tells the truth. This is just his expectation over the randomness of the outcome chosen by the mechanism when the mechanism is run with his true bid. Okay? And we can just expand out the definition of an expectation. This is just the sum over all of the outcomes the mechanism might choose, the sum over all of the possible outcomes of the utility that the buyer will get if that outcome is chosen, times the probability that that outcome is chosen, of course, given that he tells the truth. And now we can directly apply the definition of differential privacy, which says that the probability of any event does not change by much, by more than an e to the epsilon factor, if a single bidder changes his bid. So in particular, if we think about what happens if bidder I changes his bid from truth-telling to an arbitrary misreport, then the probability of each outcome O changes by at most an e to the epsilon factor. It can go up by at most an e to the epsilon multiplicative factor, and it can go down by at most an e to the minus epsilon multiplicative factor. Okay, so we can compare the probability that outcome O occurs when the bidder tells the truth with the probability that the same outcome O occurs when he lies. And these two terms are similar to one another within this e to the minus epsilon factor, which remember is roughly 1 minus epsilon. And we can just bring this e to the minus epsilon factor outside and observe that what we have left is just player I's expected utility over the randomness of the outcomes that are chosen if he lies. And remembering that, well, first, e to the epsilon is approximately 1 plus epsilon. In particular, e to the minus epsilon is at least 1 minus epsilon, so long as epsilon is less than 1. Then, and also that we've normalized all of the utility functions to be between 0 and 1. We can turn this multiplicative guarantee that the utility that he gets when he lies is smaller by at most an e to the minus epsilon term into an additive guarantee. Okay, that is, when he tells the truth, his utility is at least the utility that he would get in expectation if he lies, possibly minus epsilon. Okay, so the connection is straightforward, but that's the thing that we're gonna exploit. That if our algorithm is differentially private, then we know for sure whatever else it does, it is also epsilon approximately dominant strategy truthful. Okay. And so what we've just exhibited is a simple reduction, right? Our goal is to design an approximately dominant strategy truthful mechanism that has high revenue guarantees, but now it suffices to solve a different problem. It suffices to design a differentially private mechanism that has high revenue guarantees. So we can ignore incentives from here on out and just think about how we can obtain differential privacy in a way that is consistent with picking a price that yields high revenue. And so let's revisit this sort of straightforward approach that didn't work if we tried doing it naively. That is, instead of thinking of some kind of complicated auction format, instead of trying to be especially clever and coming up with something like a random sampling auction or the polynomial weights algorithm or the UCB bandit algorithm, like everything we've done up until now has required some clever algorithmic idea. Let's try something much more straightforward, which is just, let's just look at the bids and try to directly compute the price that maximizes revenue. Now we know that if we do this directly, like if we compute the price that exactly maximizes revenue and we do it naively, then we're going to get a mechanism that is really not truthful. It's definitely not going to be approximately dominant strategy truthful for any non-trivial value of epsilon, because it gives one bidder a huge incentive to deviate by setting the price equal to his bid. But maybe we can, pick the price in a differentially private way. Like we know that if we can pick the price in a differentially private way, then we will get approximate dominant strategy truthfulness. And so, the question is it possible to, subject to the constraint of differential privacy, pick a price that is close to revenue maximizing? And there are continuously many prices between 0 and 1, and any of them could be the optimal price a priori. But just as we've done for the last 2 lectures, we know we don't have to consider all of them. It's going to suffice to consider an appropriately discretized subset of them, so we can restrict our attention to picking a price from a finite set. Okay. And so consider the following mechanism. And this is first of all, it's going to be extremely simple. It's hardly going to be deserving of the name, mechanism or algorithm. It's just going to be defining a probability distribution over prices. And it's going to be, I'm going to give this to you sort of in the form specialized to how we want to use it now to pick a price in a digital goods auction. But this is a sort of a particular instantiation of a much more general tool in differential privacy called the exponential mechanism. And all it is the following. Okay, we'll call it the exponential mechanism. And it takes as input a couple of things. So first, it takes as input a vector V of valuations. These are the bids of the agents. It is parameterized by some discrete set of prices. It's going to select a price from the set P. And we want that this mechanism should be epsilon differentially private, where epsilon is a parameter. And so the mechanism also takes as input this parameter epsilon. Okay. And what we're trying to do is we're trying to pick the price from this set P that maximizes revenue. And remember, the revenue of a price P is just, well, the price that we get when people buy at that price times the number of people willing to buy at that price, which is just the number of people whose valuations are higher than the price. Okay, so this expression, the revenue that price P obtains on the vector of valuations V, is the thing that we want to maximize. And our sort of naive approach to this problem, the thing that we sort of mentioned on the first slide didn't work, was just to look at the bids and pick the P that exactly maximized this expression. That doesn't work. And of course, it's not differentially private because it's not a randomized algorithm. And so what the exponential mechanism is going to do is it's going to try to smoothly, according to some, smooth probability distribution, pick a P, randomly, that hopefully, although it won't exactly maximize revenue, will tend to output prices that have high revenue. And in particular, this is the distribution. The probability that we output some price P will just be proportional to e to the epsilon times the revenue that price would obtain divided by 2. And then we have some normalizing factor to make this a probability distribution. Okay, so it's a pretty simple thing. Every price has some probability of being output, but the more revenue that a price obtains, the higher the probability that we will output it. And in fact, the probability that we output some price will increase exponentially in the revenue it obtains. Okay, and this epsilon is sort of a damping factor. The smaller epsilon is, the slower we can boost the probability of outputting a price as a function of the revenue it obtains. The larger epsilon is, the more aggressive we can be. And this normalizing factor phi of v is just there to make sure that this really is a probability, that these sum to 1. Okay, so the normalizing factor is just the sum over all of the prices of this same expression. Okay, So does that make sense? We're just defining a probability distribution here as a function of the revenue of a price. Basically, we're going to randomly output a price, and the probability that we output a price will grow in proportion to the exponential of the revenue obtained by that price. So we're pretty aggressively upweighting high revenue prices and downweighting low revenue prices. So does this make sense? Are there questions about the exponential mechanism? Like, again, it's extremely simple. Basically, we're just defining a simple probability distribution, and then the exponential mechanism just outputs a sample from this probability distribution. Does that make sense? Okay. And so I want to prove two theorems. The first of which is that the exponential mechanism, with this parameter epsilon, really is epsilon differentially private. Okay, that's useful in all sorts of applications. But for us, it's useful because it will imply that the, extremely simple auction that will just look at everyone's valuation and then set a take it or leave it offer at the price that is output by the exponential mechanism will be an epsilon approximately dominant strategy truthful mechanism. Okay, and so if we can establish that the exponential mechanism really is differentially private and therefore approximately dominant strategy truthful, maybe we can improve this bound on the revenue for random sampling auctions simply by analyzing the revenue properties of this particular distribution on prices that we wrote down and called the exponential mechanism. And so let's prove it. So remember what we need to establish to prove that an algorithm is differentially private. We need to establish that for every pair of neighboring bid vectors, v and v prime, okay, and for any output, which is in this case a price p, that the probability of that output will not change substantially by more than an e to the epsilon factor if we are given input v or input v prime. Or just said another way, in this particular context, what we have to establish is that no matter how everybody else bids, if you think about what's going to happen if you bid truthfully compared to if you lie, then what we need to guarantee is that for every possible price p that we might output, the probability that we output that price p should change by only a little bit in the event that you lie. And so your incentive to lie should be very small. Okay. So this is the thing that we need to analyze, right? We've got some bid vector v. If you bid truthfully, and so the exponential mechanism gets bid vector v, there's some probability for any output price p that's the price we get. We need to show that this thing doesn't change by very much if we replace v by the vector of bids we would have if you lied. And we can just write out what is the probability that you output p. This is basically the definition of the exponential mechanism. Right, we've got this normalizing factor, and otherwise the probability that we output p is proportional to the exponential of epsilon over 2 times the revenue that we get when you bid p. And here's the important thing about this revenue function. Let's sort of go back and remind ourselves of this important fact. So remember, people's valuations are numbers between 0 and 1. And so the prices that we're going to consider, these are also going to be prices between 0 and 1. And of course, what the optimal price is, what the revenue optimal price is, might be highly sensitive to particular people's bids. We sort of saw examples a couple of lectures ago where there are these ties, there are these two prices that could be revenue optimal that are very different from one another, and if one person changes their bid, then the revenue optimal price can sort of change arbitrarily. But if you actually look at the revenue that we can obtain with some price, that actually cannot change very much if one person changes their bid, right? Because the price is just, the revenue that we get at some price p, it's just p times the number of people willing to buy the good at that price. And how much can the number of people willing to buy the good at price P change as a function of a single bidder's misreport? Well, that can change by at most one, right? Because if you change your bid, well, maybe it appears that you are now willing to buy the good at this price when you weren't previously, or maybe you are no longer willing to buy the good at this price when you were previously, but you don't change whether anyone else was willing to buy the good at this price. So the number of people willing to buy the good at any particular price can change by at most one as a function of a single bidder's unilateral misreport. And therefore, since the prices are also numbers between 0 and 1, the revenue that I can obtain with any fixed price can also change by at most one as a result of the misreport of any single bidder. And so when we look at the revenue obtainable at some fixed price P as a function of the reported bids V, this is no more than the revenue that we could obtain at bid vector V prime, if the revenue we could obtain if you misreported, plus one, right? Like in the worst case, because of your misreport, it makes it seem like price P will actually give us less revenue than it would have otherwise. But it can't make it seem as if it would have given us much less revenue. It can make it seem as if we would have earned at most $1 less as a result of your misreport, because no single bidder can have a substantial effect on the overall revenue obtained by any single price. That is, their effect is bounded by one. Okay, and so we can upper bound, because we can upper bound the revenue that we obtain at V if we use price P by the revenue that we would obtain at V prime if we used price P plus one, we can similarly upper bound the probability that the exponential mechanism outputs price P. And the nice thing about exponentials is that when I have the product of two exponentials, the parameters within them add up. Okay, so if I have e to the a times e to the b, that's e to the a plus b. And so here we have the exponential of the sum of two terms, right? There's the exponential of epsilon times our revenue over 2 plus epsilon over 2. And so we can factor out those two terms and just rewrite this exponential as the product of two exponentials. It's the product of e to the epsilon over 2 and e to the epsilon over 2 times the revenue obtainable at price P, given that you misreported. Okay, this is just the observation that e to the a times e to the b is e to the a plus b. And we can do exactly the same thing with this normalizing term. Remember, this normalizing term phi is just the sum of a bunch of terms that look like this. And so again, if we, in all of these normalizing terms, replace the revenue that we would obtain, that we would have obtained at any particular price P, given that you didn't misreport, with the revenue that we would obtain given that you did misreport, well, it can change any of these terms by a factor of at most e to the epsilon over 2. And we can pull that factor out as well. And what we get is exactly what we wanted, that the probability that we output some price P, if you tell the truth, is equal to, well, the probability that we would have output the same price P if you deviated, possibly larger or smaller by a factor of e to the epsilon, but not more than that. Okay, so that establishes that the exponential mechanism is differentially private, sort of by construction. I mean, we designed this distribution exactly to satisfy the differential privacy condition whenever revenue was low sensitivity in the reported bids. Right, the thing we took advantage of here was that a single bidder, via their unilateral misreport, could not change the computed revenue of any particular price by more than one. Okay, and given that observation, we basically just designed the exponential mechanism distribution to satisfy the property that we wanted, differential privacy. Okay, does that make sense? Any questions about this? And as we already established, this sort of also shows that the auction that corresponds to charging everyone the price that is selected using the exponential mechanism is epsilon approximately dominant strategy truthful. Okay. So we have a mechanism that's approximately dominant strategy truthful. And now the question is, okay, what revenue can it obtain? And remember, the thing that we're trying to improve on, the auction that we derived, the exactly dominant strategy truthful auction that we derived using the polynomial weights algorithm, was able to give us a revenue bound that sort of corresponded to the revenue of the best fixed price in hindsight minus the square root of the number of bidders. And so the thing that we would, that's the thing we want to improve on. And since we're giving up on dominant strategy truthfulness and replacing it with approximate dominant strategy truthfulness, we'd really like to improve substantially on the revenue guarantee, like by an exponential factor. And that's what the exponential mechanism is going to allow us to do. Okay, so first, let's state what the guarantees are of the exponential mechanism as compared to the revenue of the best fixed price, not overall, but the revenue of the best fixed price amongst the set of prices it's selecting from. And then we'll go through the usual exercise of giving it a sufficiently finely discretized net of prices so that we can compare that revenue to the revenue of the best fixed price period. Okay, so our theorem is going to be that with high probability, we have to give it with high probability bound now because the exponential mechanism is randomized. And of course, there will be some chance that it outputs any price. With some probability, it'll output the worst price. But what we can promise is that no matter what set of prices we give it, no matter what set of bids we give it, and no matter what privacy parameter we give it, we can pick our favorite failure probability delta and be guaranteed that with high probability, with probability 1 minus delta, the exponential mechanism will give us a price that is pretty good, meaning the revenue of the price output by the exponential mechanism will be comparable to the revenue of the best price out of all of the prices the exponential mechanism could have output, possibly worse by a little bit, where a little bit will be proportional to 1 over the privacy parameter epsilon times the log of the number of prices we gave it access to divided by our failure probability. Okay, so so long as epsilon is not too small, right? So long as epsilon is something reasonable, then this is a pretty good bound because it's growing only logarithmically with the number of prices that we give it access to. And so we might be able to afford to give it an extremely finely discretized set of prices. All right, and so let's prove this. So again, let's just name our benchmark. P star will be the price amongst the finite set that the exponential mechanism has access to that maximizes revenue. Okay, so P star is the revenue maximizing price amongst all of the prices that we've given the exponential mechanism access to. Okay, and now let's consider our revenue target X. Okay, and for any revenue target X, let's think about what is the probability that the exponential mechanism will give us a price that doesn't hit that revenue target. Like, let's say that a price is bad if its revenue is less than X. And now I want to think about what's the probability that the exponential mechanism gives us a bad price. Okay, well, if I have any number, any non-negative number, and I divide it by a non-negative number less than 1, I'll only make that number bigger, right? So, the first step I'm going to do, is obviously correct, but might seem sort of stupid, right? I've got this probability, it's some number between 0 and 1. And I'm just saying, okay, well, this probability, the probability that I get a bad price, is less than the probability that I get a bad price divided by the probability that I get the optimal price. Like, of course, right? Because the probability that I get the optimal price is also some number between 0 and 1. And so if I take a probability and divide it by another probability, it's only going to get bigger. Okay, but that's all that's being claimed in this first step. The probability that I get a bad price is no more than the ratio of the probability that I get a bad price to the probability that I get the optimal price. The reason, by the way, that I sort of want to do this seemingly stupid manipulation is that if you recall the probability that the exponential mechanism outputs some particular price p, it has this annoying normalization term, right? There's this sort of like pretty simple exponential expression, but then I had to like divide by this annoying normalization term to cause all of these probabilities to sum to 1. And, you know, this is sort of a generally useful trick. If I look at the ratio of two such probabilities, the annoying normalization term will cancel out, and I'll only be left with the nice term. And so that's exactly what happens in this case. So I can consider what is the probability that I output a bad price, that I output a price whose revenue is less than X. Well, I don't have to worry about the normalization term anymore because those have canceled out. And I know that for any particular bad price, the probability that I output it is at most proportional to the probability of e to the x over 2, because by definition, a bad price is one that gets revenue less than x. And the exponential mechanism outputs each price with probability proportional to its revenue. And there might be more than one bad price, but in the worst case, everything is bad. So, you know, the number of prices I'm selecting from is finite. There's cardinality of p of them. So in the worst case, every price is bad, and each of them are output with probability proportional to e to the x over 2. On the other hand, I can also upper bound the probability that I output an optimal price. Again, in the worst case, there's only one optimal price. There could be more than one, but in the worst case, there's only one optimal price, and it is output with probability proportional to exactly e to the epsilon times the revenue of the optimal price divided by 2. Okay. And, you know, just as e to the a times e to the b is e to the a plus b, e to the a divided by e to the b is e to the a minus b. And so I can rewrite this ratio, first pulling out this term, the number of prices, as well, the number of prices times the exponential of epsilon over 2 times the difference between x and the revenue of the best price. Right, like I've got the ratio of two exponentials, and so I'm just inside subtracting off their two arguments. It's the same expression. And this is true for any value x, right? Like x is sort of the arbitrary threshold at which we decided to call a price bad. And so let's pick a particular threshold. Let's say that a price is bad if the revenue that it gets is worse than the optimal revenue by exactly the amount that we sort of claimed as our bound for the exponential mechanism, by 2 over epsilon times log of the number of prices divided by delta. And let's think about what happens if we plug this choice of x into our bound above. Okay, and note that this choice of x is designed to have lots of cancellations. So first, the revenue of the optimal price will cancel out because we subtract off on the other side the revenue of the optimal price. We have this term 2 over epsilon. This will cancel with our factor of epsilon over 2. And after all of those cancellations, what we have is that the probability that we output a bad price for now this particular definition of bad is less than the number of prices times the exponential of the negative log of the number of prices over delta. And remember that the exponential and the log are inverse functions, and so we'll get yet another cancellation. This is just the number of prices times delta over the number of prices, or in other words, delta, which is what we were trying to prove. Okay, for this definition of a bad price, a price whose revenue is worse than the revenue of the optimal price by 2 over epsilon times log of the number of prices over delta, the probability that we output a bad price is at most delta. Okay. And so now we're almost done. We've got a pretty useful tool, this exponential mechanism, and we know 2 things about it. And it's got sort of 2 parameters we can play with. So first of all, there's this privacy parameter epsilon, which for us is just an approximate dominant strategy truthfulness parameter. And we can dial it up and down. We can make the mechanism more or less approximately dominant strategy truthful, meaning as we dial it up and down, we give people sort of more or less incentive to deviate from truth telling. On the other hand, we can also select a finite subset of the prices for it to choose amongst. And we know that as we enlarge this set of prices, we will get, on the one hand, a revenue guarantee that compares to a stronger benchmark, that compares to the best price amongst this larger set. But on the other hand, we will get a worse comparison. The additive error from the optimal revenue will degrade with the log of the number of prices. This is, of course, a familiar trade-off. This is the same trade-off that we made in the last 2 lectures for the polynomial weights algorithm and the UCB algorithm, respectively, when we decided to define a finite number of prices to correspond to, in those cases, experts for the learning algorithms to follow. But now our trade-off is very good, because our dependence on the number of prices is only logarithmic, and we don't have any square root terms, right? We don't have any square root terms that come with running, that come with sort of the regret that's always associated with some online learning problem, because here we're not running an online auction. And so let's walk through this trade-off again. So again, we can't we can't use this tool to select amongst all possible prices between 0 and 1. There's too many of them, but we can try to parameterize a natural discretization, all of the prices between 0 and 1 that are some multiple of alpha. And just as before, we know that as a function of alpha, the size of this set of prices is exactly 1 over alpha. And we also know that if we compare the best revenue obtainable by any price, that it is at least the best revenue obtainable by any price in our discretization, but possibly worse by a factor of alpha n. And this is again because if I take the optimal price, which might not appear anywhere in my discretization, and I snap it to the next lowest price in the discretization, I snap it to sort of the highest price in the discretization that is smaller than the optimal price, well, I will have only increased demand for the item because I will have lowered the price. On the other hand, I will have lowered the price by at most alpha, and so the revenue loss will be at most alpha per bidder, or at most alpha times n. And so we can combine these 2 bounds with the theorem we've proven for the exponential mechanism and find that our revenue, the revenue obtainable by this exponential mechanism auction, which is now a random variable because we're selecting the price randomly, will have the property that, for example, 99% of the time, our revenue will be at least the optimal revenue minus alpha times n. This is the gap between the optimal revenue of any price overall and the optimal revenue amongst the set of discretized prices we let the exponential mechanism choose amongst, minus the error term of the exponential mechanism, which degrades with 1 over our approximate truthfulness parameter times the log of the size of our discrete set. And we've got 2 parameters here, and we get to choose both of them. Okay, there's alpha and there's epsilon. You know, in our previous problems, we only had 1 parameter to optimize over. Here we've got 2. But for example, if we choose alpha to be 1 over n to essentially get rid of the alpha n term, what we find is that we now have a direct trade-off between approximate truthfulness and revenue. Okay, for any epsilon we want, we can obtain epsilon approximate dominant strategy truthfulness, and our revenue will differ from the optimal revenue by at most a factor of log n over epsilon. Okay, so let's sort of reflect on this bound for a moment, because remember, the best bound we got using techniques that gave us exact dominant strategy truthfulness was opt minus square root of n. And so, for example, if we are happy with people having, you know, say, the possibility of gaining, let's say, a 1% improvement by deviating, so epsilon would be 0.01, then this is saying, okay, well, instead of deviating from opt by a square root of n term, we can deviate from opt by only a log n term, right? An exponential improvement. And maybe we want epsilon to be even smaller than that, right? Like maybe we want to say, okay, like I don't want people to have a 1% chance of deviate, you know, a 1% incentive to deviate. I don't want them to have a 1/10 of a 1% incentive to deviate. I really want that in like a large market. And again, we're thinking of a digital goods setting. So think about selling software. You know, we might be, the number of potential buyers might be in the millions or the billions. Maybe I want the incentive to deviate epsilon to tend to 0 as the number of bidders grows large. So for example, I could take epsilon to be some diminishing function of the number of bidders, say 1 over log n. And if I do that, now I have a mechanism that's asymptotically dominant strategy truthful, in the sense that as n grows large, it becomes exactly dominant strategy truthful. And our revenue guarantee still differs from opt by at most a log squared factor now. So we're still getting this exponential improvement over the best thing we were able to do with techniques that give us exact truthfulness. And this is actually a real improvement. This sort of, you know, that it's not possible to get, or at least it's not known with techniques that give exact dominant strategy truthfulness, how to get a revenue guarantee that's as good as this. Right, so using differential privacy here has given us sort of a different point on the trade-off space where we can get strictly better guarantees of revenue, you know, better by quite a bit potentially, at the qualitative cost of giving up on exact dominant strategy truthfulness, but potentially only a small quantitative cost in that we can take epsilon to be as small as we want. So, yeah, we've really only scratched the surface here, but to summarize, first of all, differential privacy is primarily not thought of as a tool and mechanism design. It's thought of as sort of a privacy solution concept, the thing that you might aim for if you want to do some data analysis in a way that protects privacy, that protects against the ability of third parties to make inferences about you as a function of the outcome of, say, machine learning algorithms or scientific studies run on your data. But because the way it formalizes privacy is by comparing what would have happened had your data been provided to the mechanism by what would have happened had your data either not been provided to the mechanism or had your data been changed arbitrarily. It's really promising protections against arbitrary unilateral deviations, which is what gives it this connection to mechanism design and game theory, because all of our solution concepts, dominant strategy truthfulness, Nash equilibria, correlated equilibria, have been defined via this idea of unilateral deviations. And this connection goes further. So here we sort of worked out what happens in digital goods auctions, but there's all sorts of other interesting things that you can do in mechanism design with the tools of differential privacy. Typically, if you are willing to give up on exact versions of these solution concepts and settle for asymptotic versions of these solution concepts, but often with the ability to gain a much better solution than you would have otherwise. All right, so that's the end of the class. It's the second to last class. Next class is the last class, and we'll talk about algorithmic fairness. I hope everyone's staying healthy and well and enjoying the end of our socially distant semester. I'm going to stop the recording now, but I'll stick around in case there are questions.